Hello everyone. This is the second recording of presentations from the Minnesota Kernza Growers Meeting that was held March 11th, 2019 in St. Paul, Minnesota. This is Jake Jungers, faculty in agronomy and plant genetics at the University of Minnesota. This presentation will provide you with an update on some of the research findings from our program related to the basic agronomics of Kernza production. To begin, I'm going to start by giving you an overview of the Kernza life cycle. Production starts with establishment. We typically seed in mid to late August. Seeding can be done with a no-till drill or with a conventional grain drill. After seeding, the plant produces some biomass and grows in the fall purely vegetatively until the snow flies in early winter. The crop overwinters and then begins vegetative growth again in the spring in early April. The plant continues to grow by just producing leaves for a few weeks, and then in early May, stem elongation begins. Stem elongation occurs, the plant goes through anthesis, and then seeds develop and are ready to harvest by early August. Grain is harvested and all of the straw is typically removed from the field, and then the plant continues to grow, once again purely vegetatively, until the snow flies in early winter and the cycle starts all over again. The next few slides will show you some data from one of our experiments that explores the effect of seeding date on Kernza grain yield. On the y-axis is the amount of grain produced by Kernza after it was planted at various dates starting in the fall, September 1st, 2015, October 1st, 2015, December 15th, 2015, and the trial also included some spring seeding treatments, March 2nd, April 1st, and May 1st, 2016. And the Y value here, yield, was measured in the summer of 2016. So what's obvious from this figure is that when you seed intermediate wheatgrass in the spring, the plants do not produce yield that same year. And the earlier you plant in the fall previous to the first grain harvest year, more seed is made available. So here we're looking at similar data, but from the next year, 2017. So we repeated the same study, looking at harvest dates in the fall and in the spring of the harvest year. And what we see is more evidence that earlier seeding dates lead to more grain production. The earliest in this study was August 18th, 2016, and we see that there was significantly more grain yield in the August 18th seeding date compared to September 1st, September 15th, October 1st, and October 15th. This study was conducted again in 2018, but at a new location. Now we're looking at data from Roseau, Minnesota, from the 2018 harvest. Again, we're looking at grain production or yield in response to various seeding dates starting in August 15th, 2017, September 1st, September 15th, October 1st, and October 15th. And once again, our spring plantings, May 2nd and June 1st, did not produce grain yield during that 2018 harvest season. And again, these data support the finding that the earlier seeding dates result in more grain production. Now we're going to talk about the effects of seeding rate on grain yield. These data are from a trial that was conducted at 2 locations in northern Minnesota, Lake of the Woods County and Roseau County. And here we're looking at grain yield in pounds per acre on the y-axis in response to 2 different seeding rates, 6 and 12 pounds per acre. And we're looking at data from 2015, which is the first production year, as well as 2016 and 17. And one of the clear findings from this trial is that grain yields were similar in stands that were seeded with both 6 pounds per acre and 12 pounds per acre. Again, there was no statistically significant difference in yield from stands planted with these 2 different seeding rates. And this was consistent with stand age. Row spacing is another element of the establishment that could potentially affect grain yield. Now we're looking at grain yield on the y-axis in response to various row spacings ranging from 6 to 30 inches in between rows. I'm going to show you data from, again, Lake of the Woods and through various years, in this case the establishment year, 2015. So what we see here is that there is a difference in grain yield among some of these row spacing treatments, specifically the narrow row spacing treatment, which is the 6-inch row, compared to the wide row spacing treatment, the 30-inch row. Now we're looking at data from the exact same experiment, the same location, except the second year, 2016. The first thing we notice is that there's a dramatic decline in grain yield across all row spacing treatments. And in this year, we do not see a statistically significant difference in grain yield among the various row spacing treatments. In 2017, grain yields were similar to those in 2016 at the Lake of the Woods site. Again, we see no effect of row spacing in this third year in stands ranging from 6-inch row spacings up to 30 inches. I have alluded to this decline in grain yield with stand age in previous slides, and this is something that we've observed in multiple experiments across the state of Minnesota. This is data from a trial we conducted in St. Paul, and here we see that grain yields declined 69% over the course of 4 years. The 3 different colored lines represent Kernza stands that were established in 6-inch, 12-inch, and 24-inch row spacings. And what we can see is that this yield decline started right away in the second year, the second production year that is, and the yield decline occurred in stands managed with these various row spacings. This figure shows you some of the details of the effects of row spacing on grain yield through time at the trial in St. Paul, Minnesota. In 2015, we found out that grain yields were higher in the wider row spacings, in the 24-inch row spacing compared to the 6-inch row spacing. And this is contrary to what we observed at the Lake of the Woods location. However, by year 2, grain yields were similar across the 3 different row spacing treatments. But by year 4, we did start to see another significant difference between the narrow versus the wider row spacings. And then again by year 4, it's a little less clear as to which row spacing treatment produces the most grain. But again, we do see this general trend of a decline in grain yield with stand age. Lodging is a major concern for stands that are established on soils with high fertility or that get especially a large amount of rainfall during the growing season. Those conditions were exhibited in St. Paul over the course of 4 years starting in 2015. Now what we're looking at here is the lodging score on the y-axis, and that ranges from 0 to 10, with 10 being the most extreme case of lodging, where all the plants are lying flat on the ground, and 0 being the best case scenario, where there are no plants lodged at all in the stand. What we found is that lodging was worse in the narrower row spacings in the first year of the study, and the wider row spacing plots exhibited less lodging, which may explain why grain yields were higher in those treatments during that first year. There was a smaller difference in lodging score among the row spacing treatments in year 2 and year 3. And then by year 4, we saw a reduction in lodging overall for most of those row spacing treatments. Now we're going to talk about nitrogen fertilizer and managing fertility in intermediate wheatgrass Kernza production stands. From a study we conducted across the state of Minnesota in 2013, 14, and 15, we were able to quantify what the agronomically optimum nitrogen fertilizer rate was. And on average, that optimum nitrogen fertilizer rate ranged from 70 to 77 pounds per acre. So that's 70 to 77 pounds of nitrogen proved to be just the right amount of nitrogen to apply to a stand to maximize grain yield and to prevent lodging. And what we can see is that our variability increased through time. If we look at the standard error bars of this figure, which are around the mean value, we see that we become less confident around that estimate as the stand ages. We repeated the nitrogen fertilizer rate study at 2 locations in northern Minnesota, again the Lake of the Woods and Roseau counties, starting in 2015. And we applied 5 different rates of nitrogen fertilizer to Kernza stands grown in both 6 and 24-inch row spacings. During the first year, 2015, which is what we're looking at here in this figure, we found that there was no effect of nitrogen fertilizer rate on grain yield in stands managed with 6-inch row spacings. And the same goes for stands managed with 24-inch row spacings. Again, there was no effect of nitrogen fertilizer application on grain yield. Now we're looking at data from the same site, but in year 2, 2016. What we see here is that there is an increase in grain yield with fertilizer application. However, this effect is largely washed out by the great decline in grain yield with stand age. And this was observed in plots planted with 6-inch rows and 24-inch rows. Now finally we're looking at year 3. There is some effect of nitrogen fertilizer on grain yield, going beyond the 0 nitrogen fertilizer rate control up to about 54 pounds per acre, and a slight effect of nitrogen fertilizer in the 24-inch row spacing treatments as well. One way to increase Kernza grain yields by adding nitrogen fertilizer and limiting lodging is to apply that nitrogen fertilizer at different times during the growing season. One potential time to apply nitrogen fertilizer is early on in the spring at green up. This is typically in early to mid-April, which is right after the Kernza plants start growing. Another option is to apply nitrogen fertilizer in the summer after the plants have already started to produce leaves and soon after stem elongation. The idea is that the plants can use the nitrogen in different ways when it's applied at different times. And our goal is to have the plants use that nitrogen to increase seed size and yield. We started a study in the fall of 2017 at Rosemount, Minnesota. And this is a nitrogen rate by timing trial. What we're looking at here is grain yields on the y-axis in response to various nitrogen fertilizer rates and timings. And this is grain yields from the first year of the study in 2018. The red bar indicates the control, where no fertilizer was added. And if we take a look at one example of a nitrogen rate, 71 pounds per acre, here we can compare yields fertilized at this given rate, but at different timings. So our control could be considered the spring timing, which is this turquoise bar here. The purple bar is the summer timing, and the green bar is our split application timing. What we see here is that in this case, splitting the nitrogen fertilizer up when applied at 71 pounds per acre did indeed increase grain yields compared to applying it all at once in the spring. There is little evidence that splitting the nitrogen fertilizer up into the two different timings was beneficial beyond the 70 pounds per acre nitrogen fertilizer rate. The same study was conducted in Staples, Minnesota, and Staples has coarser structured soils. They're sandier, typically have less organic matter. And what we see here is that grain yields did respond more strongly to nitrogen fertilizer rates, and grain yields maximize at around 89 pounds per acre. And we also note that there's not much of an advantage to applying that nitrogen at two different timings. If you focus in at this 89 pounds per acre fertilizer rate, we actually see that applying it all in one shot in the spring produced more grain than splitting it up into two different application timings. Now I'm going to talk about some of our research that's focused on preventing and overcoming this major agronomic challenge of declining grain yields with stand age. I'm going to show you results from a study that was conducted in Rosemount, Minnesota. And again, we're going to look at grain yield on the y-axis. It's our response variable in terms of pounds per acre. And these data were collected in 2017 and 2018. And I want to mention that this stand was seeded in 2015, the fall of 2015. Grain yields were harvested in 2016. Average yield was around 800 pounds per acre from that first year. Grain yields did decline in 2017, as we can see here, between the 300 and 400 pounds per acre. But in the second year, we started to implement some of these disturbance treatments that we were thinking might help mitigate this issue of declining grain yields with stand age. So if you look across the x-axis, you'll see that each bar represents grain yields from various treatments that imposed different disturbance methods and timings. So our control plot did not receive any disturbance. They were managed as is. But we have cultivation and herbicide application that occurred just between the rows, so not over the actual planted Kernza rows. So we band sprayed herbicides in the fall, in the spring, and in the spring and fall season. And we cultivated in between rows using a custom multivator in the fall, in the spring and fall seasons. What we can see here is that there is some positive grain yield response to these various disturbance treatments, but the significance of this response is not very strong. By 2018, there is very little evidence that these disturbance methods really impacted grain yields at all. Within each of these between row disturbance treatments, we also imposed within row disturbance treatments. So within the actual Kernza rows that were planted, we either burned the residue or mowed that residue off, and the mowing was a very short stubble height type of mowing. One could call it a sort of scalping of the plants. And what we can see is that burning and mowing the residue from within those rows did not have any effect on grain yields compared to the control plots, which received no treatment. And the same trend was observed in both 2017 and 2018, which is years 2 and 3 of the stand, respectively. Now I'm going to talk about some of our research that's focused on optimizing the timing of harvest to increase Kernza grain yields. Before I explain these experiments and some of the results, we have to go over some terminology. The picture on your left is an actual photograph of a seed head, which I'm going to refer to as a spike for the next few slides. So each spike includes a number of spikelets, which are clusters of flowers that all have the potential to produce a seed. And each possible seed site is called a floret. So along a Kernza spike, there are anywhere between 18 and 24 spikelets. And within each spikelet, there's anywhere between 5 and 7 florets. What we've noticed is that the seeds mature at different rates along a spike. And we are looking to see if seeds are different in size and in moisture content in these 3 different regions along the spike, the top, middle, and bottom regions. The first thing that we're interested in measuring is the rate of seed shatter. Shattering is when seeds fall off of the spike before they are harvested. And this can be measured by counting the number of seeds along a spike or within a spikelet through time. So in this study, we went out and harvested spikes every 3 to 5 days and did just that. We dissected these spikes, counted the number of spikelets per spike, as well as the number of seeds per spikelet. And we started doing this right after this flowers were pollinated, and that we could accurately identify which florets were fertilized and would turn into a seed. And we continued to measure these variables after the seeds were very mature and dry, and indeed past the time that we would have harvested the seeds for grain. We're expressing time in this figure in terms of growing degree days. So the lower the number of growing degree days means that those data are coming from earlier on in the growing season. And the higher the number of growing degree days indicates data that came from later on in the season. And this first figure is showing us how the number of seeds per spikelet is changing through time. So this is in other words, the rate of seed shatter. And we're looking at the rate of seed shatter in seeds in the top section of the spike, which is colored in blue, the middle section in orange, and the bottom section in gray. Now we know that seeds are mature and fully developed at about 2,250 growing degree days. And that is indicated by this green line. So we would not want to go into the field and harvest any earlier than the 2,250 growing degree days, because then we'd be harvesting seeds that are not yet fully formed. We also know that we want to wait until the seeds are at a safe moisture content for storage. For Kernza, that's about 13% moisture. And from this study, we've learned that it takes about another 250 growing degree days after the seeds stop increasing in size to dry down to that safe moisture content for storage. And that is indicated by the red line on this figure. So you can consider that there's a window of harvesting opportunity. It has to be conducted after, or should be conducted after that green line, 2,250 growing degree days. And it preferably be done very close to that red line. But what we can see here is that the number of seeds per spikelet is decreasing through time, and that we are losing a certain number of seeds by waiting to harvest until or after that red line indicating 2,500 growing degree days. One way to summarize the overall net outcome of all these different changes that are occurring in the seeds along a spike, changes that include seed size as those seeds mature, the moisture content of those seeds, and the seed shatter, is to simply measure how much seed mass there is per spike. So this is a combination, again, of the number of seeds and the individual size of those seeds. And here we're looking at how that seed mass per spike changes through time, again expressed in terms of growing degree days. And again, we're representing those critical values with the green and red lines. The green line indicates the point where seeds are fully developed, and the red line indicates the point when seeds are dry enough to store safely. The plateau of that curve is what we're looking for. We want to know exactly how many growing degree days should have accumulated before we go out and harvest. And if we wait longer than that, we're going to lose yield due to shatter. If we harvest too early, we're going to lose yield because our seeds are not fully developed. So the value that we're looking for here is about 0.41 grams per spike. So about a half a gram of seed is available per spike when harvested at the right time. But how do we know when to harvest Kernza grain? Well, one way is to simply measure the number of growing degree days that have accumulated and then determine when to harvest based on those critical time periods. The 2,250 growing degree days that it takes for those seeds to fully develop, and the 2,500 growing degree days required for those seeds to dry down to a safe storage content. Another way could simply be to measure the moisture content of the seeds to determine if they are at a low enough moisture content to safely store, to harvest and safely store. To measure the moisture content of the grain, one would have to dissect a spike, pick off all of the seeds, thresh out those seeds, weigh them, dry the seeds, and then reweigh them to determine what the actual moisture content is. Another way to estimate grain moisture content is to more simply measure the moisture content of the entire spike. This can be done by clipping off spikes at the base, weighing those with a scale, a kitchen scale would do, and then putting those spikes in a microwave and drying them down using intervals of about 15 to 20 seconds, making sure to not start those spikes on fire inside the microwave. So after each interval of about 10 seconds of microwaving, the spike should be reweighed. And once the weight of that spike stops changing, we know that there is no more moisture left in the spike and that we are at 100% dry matter. At that point, we'll want to weigh the spike that's dried and then calculate what the moisture content is. And the moisture content of that spike is going to be very similar to the actual moisture content of the seed, which is data that we're showing here on this figure. This is a regression showing the strong association of moisture content of spikes compared to moisture content of grain harvested from those spikes. Now we're going to talk a little bit about how to determine when to pick up grain if you're using a swathing method to harvest. So on the y-axis is the seed head yield, and that's in grams of seed per seed head. And we're calculating this based on 3 different pickup harvest times when swathed earlier in the season versus later in the season. So first, let's just focus on the 2017 data, and that is the panel on your left. The red line indicates seed yield of a spike when it was swathed earlier in the growing season. And each point along that red line indicates what the yield was when the grain was combined out of the windrow from that early swathing date. And we can see that the later we wait to pick up that grain, the lower the seed head yield is. So we are losing seed in those windrows as we delay the pickup date. Now if you focus just on the blue line, this again is grain yields along a spike that was combined from stands that were windrowed later on in the year, so at a lower moisture content. We see the same trend. If you wait to pick up the grain till later in the year, later in August, you are going to see lower grain yields. If we shift over and take a look at 2018, it's not surprising that the highest seed head yield was in the early swathing time during the first opportunity to pick up that grain. And as we delayed into the later swathing time, into the later pickup date, grain yields declined. In this study, we have placed moisture and temperature sensors within the windrows to determine and track how conditions outside of the windrows affect conditions inside of the windrows, and then look at how grain quality changes as those conditions within the windrow change. For example, if we get lots of precipitation during the time when the grain should be drying in a windrow, what are the consequences on grain quality? What we've noticed anecdotally out in the field is that when you pick up grain out of a windrow that has received some moisture, we see issues with vomitoxin and other food quality issues. Now let's review some of the major findings from the studies that I just covered. The first major finding is that we'd recommend planting your Kernza early on in the fall or even late summer. Mid-August is a good target planting date for Kernza to maximize first-year grain yields. We also found that seeding rate has a very little effect on Kernza grain yield. In the past, we've recommended seeding between 12 and 15 pounds per acre, and with this latest bit of information, we've learned that lowering that seeding rate down to 6 pounds per acre has no detrimental effects on grain yield in the 2 locations that we've tested this. Narrower row spacings between 6 and 12 inches between rows is ideal for increasing year 1 yields, especially in these low fertility environments. However, in high fertility environments where lodging is a concern, we would recommend seeding into wider rows to prevent that lodging and to increase year 1 grain yields. After a few different nitrogen fertilizer rate studies, we have found that fertilizing with about 70 pounds of nitrogen per acre per year has optimized Kernza grain yields. It's possible that Kernza grain yields could be increased with more nitrogen fertilizer if and only if we can prevent lodging from occurring at those higher nitrogen fertilizer rates. So right now we're looking at ways to increase nitrogen fertilizer to improve grain yields while preventing lodging through altering the timing of nitrogen fertilizer application. From a few different studies, we found that nitrogen fertilizer has little to no effect on grain yield in year 1. So this may not have to be an input requirement for the first year grain production. More data is needed to determine if this is consistent. Splitting nitrogen into the spring and the summer so far does not have a major effect on year 1 grain yield. However, splitting nitrogen into a fall versus a spring timing is something that we're currently studying but have not yet received any data on. So that is a potential management practice that could increase grain yields and limit lodging. Inter-row disturbance in between these Kernza rows does not prevent a decline with stand age. So going into aging stand that is experiencing an increase in density with mechanisms to disturb the space in between the rows currently will not rejuvenate an aging stand and to bring grain yields back to a first year level. Harvest grain shortly after physiological maturity and then dry that grain mechanically to maximize grain yield. we've learned that physiological maturity is about 2,225 growing degree days. So if that grain can be harvested earlier at a potentially slightly higher moisture content, that is ideal for maximizing grain yield and preventing shattering. But again, that means that a grower may have to mechanically dry this grain. So thanks for listening to part 2, an overview of the basic agronomic practices for Kernza production. The next presentation in this series is the agronomic research update for advanced management.